Okay, so in this video, we're going to look at working with the normal distribution. So there's a couple different types of questions we'll do. We'll think about how we can interpret properties of the normal distribution without the calculator. And we'll also look at how we can use the calculator to solve problems related to the normal distribution. So one thing to remember is that there's basically two situations with the normal distribution. In one situation, you are given cutoff values and you need to find a probability. And in the other situation, you're given the probability and need to find the cutoff values. So the way you do that on the calculator will be different for each one. But regardless of what you're doing, when you think about presenting a solution, I would think about including three main things. First, always include a sketch of the distribution. This is helpful for me because it shows me evidence of your work, but also helpful for you because it helps you sort of understand exactly what to do to solve the problem. Two, you're going to have a probability statement. And so that's a statement of either what you know or what you're looking for. And then three, you're going to have your calculator values, calculator entries, and your final answer. So those are three things you should always show whenever you're doing a normal distribution question. So when you're doing a question like this, a couple pieces of information are really important. The value of the mean and the value of the standard deviation. So those are always needed whenever you're doing it on your calculator. You don't always need all of that information when you're doing it without a calculator, which we'll explore in a later question. But if you're using the calculator, you have to have these values in order to approach it. So the first question, sometimes it's helpful to be able to decode the question. So the first question is basically saying, find the probability, that's what the P means, that a value from the data is 22 or more, so greater than or equal to 22. So that's what we're looking for. What's the likelihood that if we randomly picked a point from this data set that it would have a value of 22 or more? So first thing we're going to do, we're going to sketch the distribution. Whenever you sketch it, you should always mark your mean, and it's a good habit to get into to mark a couple of standard deviations away. So if the standard deviation is 4.3, when I'm going to the right, I add 4.3, so I get to 24.8. And when I'm going to the left, I subtract 4.3, so I get to 16.2. Then I'm going to mark my threshold value or my cutoff value. So my cutoff value is 22, and I'm looking for everything more than 22. So I'm going to take that cutoff value and I'm going to shade in everything that is greater than it. And that's what I'm looking for. I'm looking for the likelihood of being in that region that I just colored in. So this probability that a randomly selected value is greater than or equal to 22 is going to be one that requires us to use the normal CDF function on the calculator. So to get there, press second, and then go to this button that says VARs right underneath the arrows. You'll see the letters above the button are an abbreviation for distribution. So we're dealing with the normal distribution. So we're going to go to the distribution menu. And then you want to pick option 2 whenever you're dealing with a situation where you're given the cutoffs and you want to find the probability. So we're going to pick option 2, and we have to tell the calculator 4 pieces of information. A lower boundary of our area, an upper boundary of our area, the mean, and the standard deviation. So if I look at the area I shaded, I'm looking for everything 22 and higher. So the lower end of what I'm looking for is 22. Now the upper end, it's best and most accurate to make the upper bound the biggest number you can get. And so we make it a number like 1 times 10 to the 99. The likelihood of having a number that large is, of course, extraordinarily low, but it covers all our bases by entering the largest number we can since we don't have a specific upper bound to work with. Now in the calculator, you can write this as 1e 99. So if you see above the comma here, there's a capital E in blue. So you can type in 1, and then you can type in that E, 99. That is the same as 1 times 10 to the 99. Just be really careful. Don't write the E notation on a test. You have to use the scientific notation with the times 10. But on your calculator, you can use it. Mean is 20.5, standard deviation 4.3. So I'm going to paste that in. It's going to give me all of this in a line. That is what I'm going to write in my solution. 22, 1 times 10 to the 99, 20.5, 4.3. Then I just press enter, and it'll give me the answer. Now, when you're doing things like this, it's helpful to write the unrounded answer first, because then I know that you still knew the answer, even if you make a rounding error. So it's helpful to write the unrounded answer first, and then your rounded answer after. So that's one situation where you have only a lower bound and you're looking for a probability. In this second example, we are given both a lower and an upper bound. So when I draw my sketch, I have my mean, I have a standard deviation on either side, and then I'm going to mark my two boundaries. So I have 18 and I have 22. And this time I'm looking for the likelihood of existing in between those cutoff values. So it's the same function on your calculator. So I'm going to give my probability statement, and I'm going to use the normal CDF function, but my values are going to be a little bit different. So when I go back to my normal CDF, I am going to have a lower bound this time of 18. That's the lowest I'm willing to go. And now my upper bound is something specific. It's not just going to be a really large number. It's going to be 22. Mean and standard deviation are the same. So I'm going to paste that in. I'm going to write down my calculator values. And then I'm going to write down my unrounded answer. And you can use dots to indicate that the number continues. And then I'm going to write down my rounded answer as well. So the likelihood of existing between 18 and 22 is 0.356, or 35.6% of the values will be between these two cutoff points. Okay, so those are some examples of using the normal CDF function. Now, this situation here is a little bit different. And the reason it's different is because we are given the probability, which in the previous examples, we were finding the probability. So we're given the probability, and we are finding the cutoff value. So the way we approach it is a little bit different, but the work remains the same. So we're still going to start with a sketch. Always has the same shape. I'm still working with the same mean and standard deviation. And this time, I have to think about the fact that I have some cutoff k, and the likelihood that I'm below k is 0.3, or 30%. So this helps you decide where you should put k on your sketch. The mean marks the 50% split. So 50% of the values are to the left of the mean, 50% of the values are to the right, and then your cutoff, if 30% of the values are below k, then that means k has to be somewhere to the left of the mean, because otherwise it would be a lot more than 30% that was below k. So here's a situation where I know that this is 0.3 and I need to find what k is. So the reason this is different is because we're kind of going in the opposite direction. So I write down my probability statement, but then I have to say, okay, now I need to do a calculation that will tell me what k is equal to. And that calculation, or that function on the calculator, is the inverse normal. So same menu, second vars, except this time I'm going to pick option 3, which says inverse normal. And now it's asking me for only 3 things this time instead of 4. The area, that's the probability of being below a certain cutoff. Now, the thing that's super important for the inverse normal is the calculator only functions if you tell it the area or the probability below the cutoff. There will be some questions, and we'll see them in a sec, where you might get the probability above a cutoff. You need to tell it below. And we'll go through an example of what that might look like with a more challenging question a bit later. For now, what we do know is below, so that's fine. We're in a good situation. So the area is the probability, and then the mean and the standard deviation are the same as what they were before. So now we get an inverse normal statement, and I'm going to write down those values as well. And again, not a bad idea to write down your unrounded answer. So 18.2450 and so on, which means k to 3 significant figures is 18.2. So 2 different approaches. Normal CDF, when you need to find the probability. Inverse normal, when you need to find the cutoff value. So those are some kind of generic questions that don't have a particular context. So let's try one where we have a real life context to work within. So here's a question where it says the heights of palm trees are normally distributed, so we know it's normal distribution, with a mean of 4.55 and a standard deviation of 0.37. So here's the thing with normal distributions. The great thing about them is that they are very predictable. So here's my mean, 4.55. This question is asking me to write down the likelihood or the probability that a randomly chosen tree has a height greater than 4.55. Well, 4.55 is my mean. And we know from the properties of the distribution that the probability of being greater than the mean is going to be 50%, because the mean is the exact midpoint of the distribution. So that's just 0.5. If the mean is your cutoff, it's 50% on either side. A big clue here was the fact that it said write down, which means it shouldn't really take much work to figure it out. The second question is reliant on the idea of standard deviations. So again, our mean is 4.55. It's asking for the percentage of trees that can exist within 2 standard deviations of the mean. So one thing to keep in mind is you could go 2 standard deviations to the right and you'll be within 2 standard deviations of the mean, or you could go 2 standard deviations to the left and you'll still be within 2 standard deviations of the mean. So we need to figure out these cutoff values. So our standard deviation is 0.37. So 1 standard deviation to the right will be what we get if we add 0.37 to 4.55. And then if we add another 0.37, we will get to 2 standard deviations to the right. And now we need to repeat that process to go to the left. So 1 standard deviation below and 2 standard deviations below. So I'm going to subtract that again. So 3.81. So the probability of being within 2 standard deviations, I can translate that into a probability statement where I say, I'm looking for the probability that I'm greater than 3.81 and less than 5.29. So 3.81 and 5.29. And that is going to be, because I'm looking for the probability, a normal CDF function. So second vars, normal CDF, my lower is going to be 3.81, my upper is going to be 5.29, and my mean is 4.55, and my standard deviation is 0.37. So when I put all that in, I'm going to write down all those values for my work, and then what I get is quite a large proportion of the data is within 2 standard deviations, which is not surprising. And remember, this was asking for a percentage. So the percentage is just going to be the probability times 100. So 0.954 times 100 is going to be approximately 95.4% of trees will be within 2 standard deviations of the mean. So in that one, we're still using the normal CDF, but we kind of had to figure out our own cutoff values before using it based on the information given in the question. Okay, next part. Likelihood that a randomly chosen tree has a height greater than 4. So I'm going to draw my little sketch. And then I'm going to realize that 4 is going to be below 4.18. And I'm looking for those that have a height greater than 4. So that'll be all this part of the curve. So greater than 4 meters. That's going to be another normal CDF because I'm looking for the probability. And I'm going to put my lower bound at 4 because I want everything above 4. And my upper is going to be 1e to the 99. 1 times 10 to the 99. Mean and standard deviation are the same, so I can leave those together. I'll have 4, 1 times 10 to the 99, no e's, 4.55, 0.37. And again, that's quite a large proportion. And this time, notice that it was asking for a probability, so there's no need to convert it to a percentage here. I can just leave it as a probability, rounded to 3 sig figs. Okay, so that was pretty standard. The last part gets a little bit trickier. So notice it's asking me for the minimum height of the tallest 25%. So I need to find the cutoff when I'm given the probability or given the likelihood. So remember, when I need to find the cutoff and I'm given the probability, that's a case for the inverse normal. So let's sketch this out. So 4.55, I'll put a couple standard deviations on either side. Now, the tallest 25% is going to be on the right side of the mean because right at the mean or exactly to the right of the mean will be the biggest 50%. So if I want the biggest 25%, let's say I'm somewhere over here. So let's say that's K. This will be the biggest 25%. Now here's where the trick comes in that I was talking about earlier. The calculator function only really works when you give the calculator the probability of being below the cutoff. So what I have to translate what I've just drawn into is knowing the probability below a given cutoff. So if 25% of the data lies above K, then by definition or by the axioms of probability, 75% of the data must lie below K. And this is the really important piece of information I need for the calculator. So when I do this on the calculator, I'm going to say, okay, I know the probability that a randomly selected value is larger than K is 0.25. But I also know that to find K, I need to use the inverse normal function with a probability of 0.75 because I have to reverse it. I have to get the probability below. So when I go to inverse normal, I'm going to put 0.75 as my area because the calculator only processes the below part. And I'm going to put the mean and I'm going to put the standard deviation. And when I do that, I'm going to write down the values I put in to the calculator, and I'm going to get my value of K, which means K is approximately 4.80. So the minimum height of the tallest 25% is approximately 4.80 meters. And that makes sense, right? Because the tallest 25% would have to have a threshold height higher than the mean at least. That's the only way it would work. Okay, so let's go to the next set of questions just for a bit more practice. So residents of Happyville we're looking at their savings, mean of 3,000, standard deviation of 500. So what percentage of residents have savings greater than 3,200? That is going to be a case where we are given a cutoff and we want to find the probability. So that would be a case for normal CDF. So I'm going to have 3,500 over here. I'm going to have 2,500 over here. And I'm looking for 3,200. And I'm looking for everything above 3,200. So probability of having savings greater than $3,200 is going to be normal CDF. And this time my lower bound, 3,200. My upper bound, I don't have a specific value, so 1E99. My mean and my standard deviation. Oops, not 5,000, 500. Make sure all your values are correct. I'm going to write them down. 1 times 10 to the 99. And then we'll get our solution. So once you get in the habit of this, it actually goes quite fast when you're comfortable sort of selecting which process you're going to use. And because there's not a lot of work to show for these, right? You just kind of have to show the sketch, show the statements, show the answer. But selecting the right strategy can be tricky. Now, again, this question was asking for percentage, so I'm just going to multiply that by 100 to get approximately 34.5%. Okay, now we are given an upper and a lower bound. So we're looking for the likelihood of having savings between 2,300 and 3,300. So 2,300 is going to be over here. 3,300 is going to be over here. And I'm looking for this area in between. So again, looking for a probability, which means I am looking for normal CDF. So normal CDF, now I have a lower bound of 2,300 and an upper bound of 3,300. Mean and standard deviation remain the same. So I've got 2,300, 3,300, 3,000, and 500, which gives me 0.644, which when I round gets me actually 0.645 because it's 6,449. So that's the probability that this resident's savings are between 2,300 and 3,300. The last one, we're looking for a cutoff value and we're given a probability. So this sounds like a case for the inverse normal. So we got 3,000. And what we're looking for is a cutoff where below which we have almost 3/4 of the data. So I think that cutoff's, oops, they asked us to label it D, so I'll do that. I think that cutoff's going to be somewhere over here. It definitely has to be to the right of the mean in order for this to make any sense. Because 50% would be in the middle, and then so 75% would have to be past the middle, and that will be the area I'm shading. Or 74.22%, I should say. So this area is 0.7422, and because we're looking for the area below a cutoff, there's nothing I need to change, no values I need to subtract. I'm already looking for something below a cutoff, so I can just do the inverse normal as I normally would. So I'm going to give a probability statement. So what I've been told in the question is that the likelihood of being below a cutoff of D is, I'm going to translate that percentage into a probability. So I just divide by 100. And then D, therefore, is going to be the inverse normal of a set of values. So when I go to inverse normal, I am going to do an area of 0.7422, a mean of 3,000, and a standard deviation of 500. So I'm going to write those values down. And then I'm going to let the calculator tell me the answer to that. Now, because of the context of this situation, which involves money, the rounding that I should be doing should be to 2 decimal places. So I'm no longer going to do the 3 sig fig rule. I'm going to do 2 decimal places because I'm talking about an amount of money. So therefore, 74.22% of residents have savings less than 3325.07, and I think that's measured in dollars. So I'm not always putting my therefore statements in these questions, but I'm trying to illustrate occasionally what they should look like. Okay, home stretch, one more question. This question is really interesting because you'll notice that you only get the mean. We have not told you the standard deviation. And that's okay because we can use some of the properties of the distribution to figure out the answers to these questions, even when we don't have the standard deviation. So the other piece of important information we get is that the probability that a height is greater than 24 is 0.06. So here's my mean height, 17. So somewhere over here is 24. And that, based on the information I highlighted in blue, the likelihood of being above that 24 is 0.06. So what's cool is the likelihood of being below that 24 has to just be the rest of the distribution. So being less than 24 is just going to be whatever remains within the distribution that isn't what I shaded in blue. So if the probability of being less than 24 meters tall will just be 100%, or 1, because that's the whole distribution, minus the probability of being greater than 24 meters tall. But we know that the probability of being greater than 24 meters is 0.06. So if 6% of the data are above 24, then that means 94% of the data will be below 24. So we didn't actually even need the calculator for that. We just relied on the idea that all the probabilities for a normal distribution will add up to 1. And that's sufficient to be able to solve a problem like this. Okay, so the idea that all the probabilities add up to 1 is one key element of the normal distribution. Another key element is that the normal distribution is symmetrical. So again, if we draw this normal distribution, we mark our mean of 17. We know that the cutoff of 24 gave us a percentage of 6% of values above 24. So now it's asking us about the likelihood that a tree has a height less than some other cutoff is also 6%. So if we're above 24, the probability is 6%. If we're below something else, the probability is also 6%. So again, when things are normally distributed, there's a symmetry there. And the symmetry means that whatever the distance is between 17 and 24 to get to my upper 6%, I have to have the same distance between 17 and D to get to my lower 6%. So 24 minus 17 is equal to 7. And so to get from 17 to D, D is going to equal 17 minus 7. So 24 was 17 plus 7. D will be 17 minus 7, which means D is going to be 10 meters. So 6% of trees have a height less than 10 meters. Okay, so again, no calculator required, just relied on the properties of the normal distribution. And the last part combines some nice skills that are important to know. So in this last part, first of all, we need to find a number of trees. So this is no longer a probability, it's actually a number of trees, and we need to find it within a certain range of heights. So we're going to use the information we had from the previous question. So we had 6% that have heights above 24 meters. Another important thing to know is that the mean marks the halfway point. So everything above the mean for the rest of the distribution, that area would be 50%. And so if we've already accounted for 6 of that 50%, then what remains must be 50, which is the whole upper half of the distribution, minus the 6%. Or maybe I should express that in decimals, 0.5 minus 0.06. And that's going to leave us with 44% of the data in between 17 and 24. So again, not using a calculator really, but using the properties of the distribution. So notice that 44% of trees are between 17 meters and 24 meters. But it wasn't asking us for the percentage, it's asking us for the expected number. So if we have 200 trees and 44% of them are between 17 and 24, then we need to know what is 44% of 200. We need to know how many trees is this? How many trees? So to do that, we simply multiply. So we're going to do 0.44 times 200. And when we do that calculation, we get exactly 88 trees. So 88 trees are between 17 meters and 24 meters. So I guess I'd probably summarize with some key features of the distribution, right? So if we have a random normal distribution with a mean of mu, then we're going to have 50% of the data on this side and 50% of the data on this side. So this is going to be 50%. This is going to be 50%. All of it together is 100%. So you can think in percentages or you can think in decimals. So 0.5 and 0.5. Maybe I'll do that in a different color. So if you want to think in percentages or in decimals rather, then your total would be 1 instead of 100. And it's also true that the distribution is symmetrical. So if you know about information on one side, you know about information on the other side. If you're given cutoffs and want to find probability, then you use normal CDF. If you are given probability and want to find cutoff, then it is inverse normal. So this is option A, this is option B. Remember though, only works with probability below cutoff. So you sometimes have to translate if you're given a probability above a cutoff. You have to flip that around and figure out the probability below the cutoff in order to use it in your calculator. Okay, so hopefully that was a helpful video to help you navigate questions related to the normal distribution.